Hey, this is Dr. B. Here I am right here and right here. And I will be talking to you about week one at Rasmussen College for those of you taking Chemistry 1100C with me. Here's the things we're going to go over, and it is quite a bit. It will take the better part of an hour. And let's begin. We're going to be talking about why chemistry is awesome, one of my favorite topics. We'll have a look around Blackboard, take a look at the syllabus, see what's due when using the calendar, take a look at some resources that are available to you, and go over the repeating procedure we'll be doing each week where we submit the assignments, they get graded, and then the following week you do it all over again for 6 weeks. So that's the overview. We're also going to talk about the core material for Unit 1, and that's coming up. You are taking this course to study chemistry. The majority of you are nursing majors. Chemistry is a foundational course that I think will help you. You do get to blow stuff up. This is an online lab, so I'm afraid it'll be virtual only. Chemistry can provide very deep answers to questions since it goes right down to the molecular level. If you are trying to make a difference for the better for the world, you're in the right place. This is a pathway towards understanding things like cancer, pain, disease, retroviruses, correlating the structure of remdesivir to its activity and its mode of action, that sort of thing. That's what chemists do, and that's what chemistry allows you to look at. It's a gateway to all sorts of great fields: medicine, engineering, absolutely nursing. And let's have a look around. Most of you are familiar with Blackboard. Typically, you'll see on the left this group of topics here. If you don't see it, there's a little puller over here that you pull on and get it to show up. Make sure you're in the summer 2020 course. You can take a look at your grades. You can have a look at the discussion board. Please do post something to the discussion board to introduce yourself. And if you're struggling with anything, the general discussion is a great place to go to. The syllabus is here, an electronic textbook, etc. So all these things are available. I'm not going to spend too much time on it since most of you are already familiar with it. There's at least 3 posts already on the announcements, including this entire PowerPoint that I'm basing this discussion on, not only for this week, but for the entire week. So new this term will be some templates that you can use to submit your assignments, and I hope it makes it easier. Here's me, here's my contact information, sending me an email at any time for any reason, and there you go. The course consists of 6 modules. Here's the introductory material. They call these assignments for our first unit. Now, until you get to where it says module, none of them have any point value, but you'll never get through these modules unless you go through them. If you're an experienced chemist, I'd suggest, with experience in chemistry courses, I should say, I would suggest you peruse these briefly, if at all, and try diving right into the homework. If you go through these and don't like what you see, you may prefer to try my videos, and I'll show you those for each of these topics. Not every single one, but just about. But I find that these brief summaries are to the point and very useful, so I suggest you take advantage of them. Everything in this weekly assignment is due Sunday before midnight, so be careful. See the time input here? Don't find yourself being Saturday afternoon and you still haven't started the real assignments. Where it says module here, these are the real assignments with point value, and that's what you're graded on. There you go. In the upper right-hand corner of the Blackboard, you will see the calendar. This is from a previous semester. I've moved the live discussions to Monday evening at 7 p.m. That's where we'll solve some real problems and go over the core material. New for this term, I'll be spending more time doing problem solving so that you can get right into the nitty-gritty. Everything's due Sunday just before midnight, and you'll receive the packet for the week on Monday morning. If you peek at that PowerPoint slide on which this is based, you'll see that it covers the entire term. Since this is PowerPoint, if you feel like printing this out, feel free. Just download it and print it out. If you'd like access to some of the common formulas, they're on this sheet, and you can print that out as well. Here's an overview of the course in terms of how it's broken down. You'll see it's a roughly even distribution of assignments, labs, and quizzes with a couple of other things. For example, there's a 15-point classroom assignment where I give a passphrase during the live classroom and you have to write it down. Here's how every point is accumulated for this term. There are, I believe, is it 230 total? Well, no, it's much more than that. But all of these points that are accumulated are done so by the week. So we have Module 1, think of it as week 1, and right to Module 6, which is simply the final exam. And here's how it's broken down, and you'll see for each week those scores are broken down as well. So there should be no surprises as to where each point comes from. And here we go. This is week number 1. Once I'm done recording this video right now, I'm going to put the link here so you can click and watch this, what I call pre-recording. When we do the formal live classroom at 7, it will be similar, but I know you guys have all sorts of different schedules, so if you can't watch this thing, you can watch the pre-recording that we're doing right now. Here is what you'll be learning this year. It's a surprising amount of material. This is for this week, I should say. Here's a suggestion how to divide up your time for the week. We'll be meeting Monday at 7 for the video. Here's a pre-recorded link to it here as well as here. This suggests that by Wednesday, get into the scored material, that being the first lab. You can start it earlier if you want. We have 2 labs, an assignment, and a quiz for the first week. Here's the topics that you'll be learning. If you don't like the way they are covered on Blackboard, I would suggest watching these optional videos. They're just a few minutes each. That could help you. And here is the actual scored things right here. If you start Module 1, Lab 1, and you don't know what's going on, consider watching these help with the lab videos that are designed to assist you if you're struggling with either the nuts and bolts of, like, the administration of these things, or if the core material is not making sense with you. Same thing for Lab 2 and the assignment and the quiz. So lots of help is available in the form of short videos. I said the scoring was broken down for each major assignment, and there it is. So no surprise there. For each of these things, you'll be submitting an assignment to Blackboard. Here's Blackboard's video on how to submit an assignment. I'll have more to say on this. Bear with me, though, because in the next slide, you'll see some templates for each assignment designed to streamline the process. Here is the link for when you go online. Just click on that, and at 7 p.m., you and 34 of your best friends will be online listening to me give this talk. I'll give it in a slightly different fashion so that we can emphasize real problem solving on scored assignments. Okay, here's the very first assignment for which I've made a template. Notice that it's 2 pages long. You go to this website, you do some virtual pouring of various mixtures, and you write down amounts each time. These each have a scoring value, and this one is solved for you. I usually solve 1 or 2 problems to get you rolling to see how to do things. And when you click on these links here, in fact, I'll show you. When you click on these links here, they're designed to give you a red color and very clear that you answered the question, and very easy for me to grade because everybody's got the same thing in the same place. So submit using these templates, and I think it's the most direct way to do things. It'll also include common errors, things like that. Here's the second page. When you're doing anything that involves mathematical transformations like this, don't just write the answer, always show your work to get credit. And here's an example of a good example of shown work. I don't require that you type these things, although it is designed to do this directly, so you might want to take advantage of it. You could print this out and write your answers by hand in here. You could write your answers on a separate sheet of paper if you want. But be sure to follow the instructions. Show all work for solved mathematical problems. Here's the second lab, which involves a data sheet which you can fill out, and a screenshot of a completed lab, which you could put right there and then submit it. More on, the assignment here. This has a rather high point value. It looks like it's 2 pages long, so fill in the blanks and off you go. Okay, it's now time for the core lectures. Now, I'm really going to have to be very brief here. Be aware that for each one of these, you can watch a pre-recorded video that I've prepared over the years for each little mini topic here. But I'm going to go ahead and cover these briefly, and very briefly, and then any remaining time would be available to solve real problems. The first topic is a math review. Now, for chemists, they need math, no doubt, because they need to use numbers, but those numbers are not just abstract typically. They represent real things. That being the case, there's more to math for chemists than just a number. Let's do an example. Say you got this graduated cylinder full of ethanol, and the question is how much ethanol is in the cylinder? Well, that's milliliters. It's above 6 milliliters. It's above 6.6. It's less than 6.8. The rule is to estimate one digit, so I'm going to estimate 6.7 milliliters of ethanol. Notice that this answer, when you're using numbers, normally consists not just the number, but 3 parts. The number itself, the appropriate unit of measure, and the appropriate level of precision, 6.7, not 6.735, not 6, and the label of what in fact it is, in this case ethanol. Another thing chemists use numbers for is to manipulate these numbers using formulas. Here's an example. What is the mass of ethanol in that graduated cylinder given its volume? Well, you're going to have to look up its density because density equals mass over volume. Let's rearrange that since we're asking for mass. Mass is volume times density. And then let's solve it plugging in not only the number, but also the unit and the label. Cancel it out and bring it into another unit because it's true that every milliliter has a mass of 0.71 grams. I looked it up. Notice that milliliters over milliliters cancels, and we have an answer now in grams. We also have a reasonable level of precision for this. There it is with too much precision. If we only are accurate to the 10th, I doubt we can give an answer that's accurate to the 1000th. And in fact, we have 4.8 grams of ethanol solving this problem. Let's talk about the scientific method briefly. If you remember, oh heck, I know that, it might take you most of the way. Observation, hypothesis, experiments, and conclusion. We begin with an observation, wondering why. We then offer a reasonable estimate for what that might be due to. We do some experiments to see whether we're right. Those experiments have controls built into them, which are standards for comparison. They can be either a positive or a negative control. So you have something to compare it to, and so that you're not deluding yourself. We run into a conclusion, or perhaps not. It begs some more experiments, and the wheel goes round and round. An example of a positive control would be like aspirin if it was for a pain medication. You could see whether your medicine is more powerful or less powerful than aspirin. We also could use negative controls, not always, but occasionally. A placebo is a good thing to do to make sure you're not impressing people and biasing their opinions. From small amounts of evidence, we can get a hypothesis, which is just a tentative explanation. Once we have a lot of those, we can come up with a theory, which is a unifying principle that explains more than one fact and or law. And once you're certain that that theory is always, always true, we can call it a law itself, which is supposed to never be untrue. When we're dealing with data, it's also nice to know that data can be of the qualitative variety, which is less useful with no numbers, or the quantitative variety, which does have numbers. All numbers have associated units with them. We used milliliters and grams already. Here's the initials. Maybe you can guess what they're for. I'm going to go pretty quick. K is for Kelvin, a unit of temperature. The S is for the second time. M is for the meter, which is distance. Kg has a prefix in front of it for some strange reason, but the kilogram is a unit of mass. CD you'll never use. It's the candela, a measure of brightness. MOL is quite common since that's how chemists typically count things that are very, very small. It's the mole. An amount equal to 6 times 10 to the 23rd. And an ampere is an electric current. And there you go. Those are the 7 SI units. From them we can derive others. For example, speed is meters per second. And that's a derived unit, meaning it's two primary criteria divided by one another. Acceleration will be meters per second squared, derived unit. Volume could be length times width times height, for example, so it's distance cubed. That's a derived unit, therefore. And density can be grams per milliliter, derived from grams as well as milliliters, which are the primary SI units. The only formula we need to know so far is density is mass over volume, and we've already shown an example of that. Unit conversions is central to understanding chemistry. It allows you to switch from one unit to another. For example, if you have $7.25, I'll bet you know that you have 29 quarters, but let's see how we could get that systematically. We'll start with what we're given, which is $7.25. We recognize that all we have to do is 4 quarters to a dollar, a one-step conversion. And let's put dollars on the bottom. Every dollar is equal to 4 quarters. Do the math and you'll see we have 29 quarters. But how many dollars do you have if you have 12 quarters? Well, you might know very quickly to divide it by 4, but let's make sure. Start with what you're given. Draw a line. Should be a one-step conversion. 4 quarters is a dollar. Yeah, that seems true. Quarters over quarters is 1. I like the way it's arranged. And it turns out we have $321.25. 65 miles an hour is a certain number of meters per second, but I don't know if I could guess it. Let's change miles into meters. Let's change hours into seconds. 65 miles per hour, but a mile is 1,609 meters, and there's 3,600 seconds in an hour, so we should have converted from hours is gone, miles is gone, meters per second. Yes, that's what we want. 29. Part D. Here's a harder unit conversion. Most gases occupy 24 liters per mole at room temperature, so we'll write 24 L over mole and recognize that that is generally true. Given that carbon dioxide has a molar mass of 44 grams per mole, what's the density of carbon dioxide at room temperature in grams per liter? Well, we know that 44 grams per mole is about the density, grams per mole, is the molar mass of carbon dioxide, 1 C, 2 O's. And we know that a mole of it has a volume of about 24 liters. Notice that moles are gone, so we have grams per liter. That might be pretty good. 1.8, we'll round it down to 1.8 grams per milliliter is the density of carbon dioxide. Another important topic is significant figures, which gives people an idea of how much precision to use when working with numbers. Here's an example of a volume, which we always measure the bottom of the meniscus. It appears to be 32 milliliters is the unit, but should we report 32? The rule is to estimate a digit, and that would mean since we're accurate to the single digits, we'll estimate a tenth, but I don't even think we have 32.1, so a good answer here would be 32.0 milliliters. And this shows us that when measuring, we always include the known digit plus an estimated one. Line up parallel to the meniscus to prevent parallax, meaning you'll get an inaccurate reading if you're too high or too low. A device such as this minimizes it by making it so you cannot see the reflection when you are lined up, so there is no parallax. This number has two significant figures here. Since both the 3 and the 2 can not be represented any other way, we could also say this is accurate to the whole number. This number is accurate to the 10,000th. However, it only has 3 significant figures because we always can drop the leading zeros. This can be represented as 3.23 times 10 to the minus 2. Sandwich zeros are always significant. You cannot represent this number without those zeros in between. If you have zeros at the end called trailing zeros, we keep them if there is a decimal place, as in here, 3 significant figures. It might be assumed that this is a very rough number unless the decimal place is there, so we use that rule. Here's an example of both central and trailing zeros. We do have a decimal place, so I see 5 significant figures there. Putting it all together, you can see that this number has all significant figures except for the leading one, giving us 5 significant figures. What about when you're doing mathematical transformations? If you're adding and subtracting, you're never better than your roughest number. Therefore, this one should be only reported to the 10th, meaning that we have 7.46, but we'll report it as 7.5 by rounding up and being accurate to the 10th. If we have a number such as this and we want to represent it to 2 significant figures, we have to round up to 2.3. So when it's 5 or higher, round up. This number may appear to be 2, but it's accurate to 3 significant figures, therefore 2.00. The rule for multiplying and dividing is not to keep the fewest number of decimal places, but rather the fewest number of significant figures. Tedious? Yes. Infinite significant figures are assigned to anything that is counted or exact. For example, 12 inches is a foot, or there are 3 oranges in that bowl. Should you round as you go? No. You should always carry at least one extra decimal place for longer calculations, then round at the end. How many should you carry at the end? At least one. And for combinations, get the raw number and then apply the more stringent rule at the end. Coming up with this number here, this within the decimal, first we do PEMDAS, so within the parentheses we have this, we multiply it by 33. We get a raw number of 268.653. However, there are only 2 significant figures here, therefore the final answer is 2.7 times 10 to the first, or 270 without a decimal place. A lot of details there. That is significant figures. Density is a sort of relative heaviness of something, isn't it? Given the same volume, what's heavier? If it's the same volume and one is more heavy than the other one, we say it's more dense. So it's mass divided by volume. As long as we're talking about density, it's good to know some rough numbers. Gases tend to have densities of about 1 gram per liter, which is a cubic meter. Liquids tend to have very roughly somewhere between, I say a half and 18 grams per milliliter, or kilograms per cubic meter. And solids tend to have densities of similar, right? Probably higher than 1 in general, up to as much as 18 grams per milliliter. Let's do a couple calculations. If we have 13.5 grams of aluminum and we have 5 milliliters weighed out for that 13.5 grams, I'm sorry, not weighed out, but volumetrically determined for that 13.5 grams, well, it's direct plug-in. Grams per milliliter, 13.5 divided by 5. Best, of course, to include the units themselves, and we get grams over milliliters as we must, and that's 2.7 grams per milliliter. Here we just wanted to show that it's a nice rule of thumb to compare the density of anything to water. So you could say it's a floater if it's less dense, a sinker if it's more dense. If you had 2 mils of aluminum, it would sink. Notice this is greater density than water, and that mass would be less than 2 milliliters, would it not? And so we say density is mass over volume. Mass is therefore equal to volume times density. We take the volume of 2 mils, multiply it by the 2.7 grams per mil, and we get grams directly. It tells you that is correct for 2 reasons. one, we predicted an answer of greater than 2 grams, and in fact, the units also cancel. So that reinforces it from both of those directions. 5.4 grams is reasonable. And that is the required material for week number 1. There's also a bit to be learned about energy and a bit about safety. However, I'd recommend you just do the reading for that because they cover that in only a cursory level. All right, so if you know that material, you are good to go. Solve the problems for week number 1, and off you go. If you attend the weekly meeting, we're going to dive right into solving lots of problems, and you should be ready to go there. Okay, welcome to Chemistry 1100C. I'm Dr. B, and remember, all assignments are due Sunday before midnight.